Hello everybody and welcome back to another video. I know it's been a little while, but I wanted to get a video out there, and I know that we said this was going to be an interactive STEM channel, so today I have something interesting here. So today we're going to be talking about building an amusement park ride. Not very professional one, but still it's going to be fun. And then using that to kind of determine some physics things. So now let's say we have these equations here and we want kind of a ride that kind of goes, let's see, it kind of goes like this. And then there's a bucket here or something. And this isn't going to be a very safe ride, but it's still a ride. So we have a little car here or something, like a roller coaster. And it goes up here, it flies off, and it lands in this bucket. So that's basically what we're going to be modeling today. So if you're building this at home, you might want to use cardboard to create this ramp. And then you're going to want something that slings the car or just pushes it. You could push it if you wanted to, no shame in that. So if you're doing that, you might want to have like something like this, and then you have rubber bands tied, and then you pull it back, the back of the car's against it. So I guess this should be a little lower because the car would be smaller. But you pull it back, it shoots the car, and then the car lands in a bucket. Seems pretty simple to build. Personally, me and my friend did this for a lab a little while ago, and it took us a little while to build, but that's because we didn't come in it with that kind of idea, right? We had a bunch of ideas, but ultimately we decided on this idea of something with like a slingshot kind of thing, and then a bucket, right? So it shouldn't be too hard to build. You just kind of got to think about like, well, where would the things go? And if you're using these equations, it's very important that the ramp is like this, right? It's straight. You can't have it like curved. So I know like technically it might be better to go kind of like curve like this and then up, but that kind of takes away from these calculations here. So let's say that we have this example. So let me draw it out. So we're gonna say that you built your ride, and this is kind of what it looks like. So you have a slingshot, and you're slingshotting the car or the rail thing at an initial velocity of 2 meters per second. That's what the V0 means. And then we're going to say that the slingshot, or where the car starts, is at x and y equals 0. So both of them equal 0. And then we're going to say that this ramp is angled like 30 degrees up. So now, well, we're going to try and find some things. So really what we have to determine is, well, how does the velocity change here and like from this 2 meters per second. So to do this, we're going to assume that there's no friction and that the car is like not being pulled down as it goes up here, even though it would in real life. But we're just going to assume it's not, just for the simplicity of this experiment, because this is supposed to be like an entry level thing. So how do we find the x direction of the velocity here? Because this is going up, and this can be broken down into both a x direction and a y direction, because it's going both up and to the left. So how do we find that? Well, if you know your unit circle, then you might say, well, trig. So, and that would be correct. So to find v of x, we do v times cosine of theta, and theta is this angle here. And to find y, it's going to be the other one, so v sine of theta. So in this example here, we're assuming that the v is like, the total v is like constant throughout. So v0x is going to equal 2 cosine of 30. Now, these equations are like just because you're kind of like projecting it. So you're taking this and you're projecting it down to the x, right? So that's where this comes from, and then this one you're projecting it like to the y. I don't really have an explanation for that beyond that, but you don't really need one. You kind of just got to memorize them. So 2 cosine 30, well, if you know your trig, then that's going to be 2 root 3 over 2, which equals the square root of 3. Now, this is just like you can plug this into a calculator. Yeah. So v of y is going to equal then 2 sine of 30, which if you plug that into a calculator, you would get 2 over 2, which equals 1 meter per second. And if you know how vectors work, then, which you don't have to for this, but if you did know how vectors would work, you would know that the total velocity would equal like 1 squared plus the square root of 3 squared, which is 3. And then that's just 2. So you see they're equal. So we just broke it up. Now, we're going to say that our time starts here, okay? And we need to find that time. So how do we go about finding the time? Well, you see how we have this equation here. Now, what if we changed x to y? Because we have it's two-dimensional. So what if we say y equals y0 plus vy0 plus 1/2 a y t squared? Well, let's say that this is 1 meter above the ground. So now, what do we say then? Well, if we're assuming the car, this is where we're starting our measurements from. Then we would say that y equals 1 plus, we know our v of y is 1, so we can just plug in 1, so this cancels out. So t plus, and then a in the y direction is always going to be g if we ignore air resistance. So this is going to be negative g, and the reason it's not positive g is because it's going down, and down is typically negative. So negative g over 2 t squared. Now, if you know g, let's say it's 9.8. So for our example, let's say g over 2 is 4.9. So now we have to say, well, how do we find t? Well, we're trying to find when it goes in the basket, which is going to be when it hits the ground. And the ground is going to be when y equals 0. So we get 0 equals 1 plus t minus 4.9 t squared. Now, this is where some kind of algebra comes in. So, like, if you're doing this with your kid or your kid doing this, you might not necessarily know this, the quadratic equation, but a lot of people do, and that's okay. So I'm just going to go through it here. So we have the quadratic equation. In this case, our variable is t. So we're going to say t equals negative b plus or minus the square root of b squared minus 4ac over 2a. And then just for reference, our b is our coefficient of this t. So we say that b equals 1. Our c is our constant, which in this case is also 1. And our a is the coefficient of our t squared, which is going to be negative 4.9. So what is our t going to be then in this case? Well, we're going to get t equals negative 1 plus or minus the square root of 1 squared is 1 minus 4 times 1 times negative 4.9 over, and then our g was 9.8, and that's just 2 times this, so negative 4.9. So we're going to say that t equals, we're just going to flip the negative, so 1 minus plus the square root of 1, and this just comes from like flipping you know, just flipping the negative. And actually, let me just put this in the calculator so that we don't have to write it all out again. So give me a second. So we get 20.6 over 4.8. Now, t is always going to be positive, and if we subtract 1, so we do 1 minus the square root of 20.6, well, that's going to be less than 1, and that's just because the square root of 20.6 is greater than 1. So we can't have that, because then t would be negative. So we can ignore the negative, and we can say this goes to 1 plus the square root of 20.6 over 4.8. So what is that going to be? Let's see, 1 plus the square root of 20.6 over 4.8. We get t equals, let me write it up here. So we get t equals 1.154. Let's just say that, seconds. Because this is it's going to be in meters and seconds, just because that's what these equations were made from. So let's erase all this work. Now, remember that you're probably going to be doing this with like your own thing, and that's fine. Oops, I didn't want to erase that. So, you know, change the values to fit yours. And then, so we have this, and now what I want to do is I want to find out how far the car goes. Now, this is just for fun. Like in my lab, I had to do this for a lab. We had to find some more things, but these equations are just going to be for fun. We're going to see, what is it? How far it goes, right? So now we can use the actual form of this x equation. Well, our x0, we're going to assume is still 0. Just because we'll say the initial point is 0. So actually, let me erase this, and let me change it to over here. Yeah, it's probably a better way to write that, but doesn't matter. So our vx of 0, we wrote down here, is the square root of 3. So we're going to have t times the square root of 3. And then in a problem like this, where we're ignoring like air resistance and all that, we're just going to assume there's no acceleration and that the velocity is constant. So we can say our x of 1.154, which is what we calculated as our time to hit the ground, is going to be 1.154 square root of 3, and then so that's going to go to about 1.999 second or meter, sorry. So basically, if we're ignoring air resistance in that, you'd want to put the bucket like 2 meters away from the thing if you were launching it at 2 meters per second up a 30 degree incline, and assuming this was like a meter, assuming that it's still 2 meters per second up here, right? So there's that. And then, you know, for fun, why don't we just say what the highest y value is going to be? Well, we know, well, it's known that when the velocity of y equals 0, so we say vy equals 0, is when y is at its highest. And it kind of makes sense, right? Because it goes up and then down, right? So it's rising, it's rising, it's rising. The velocity is positive, and then it hits the peak, and the velocity stops, so it stops moving, and then it goes down, down, down. So the velocity is decreasing. So why don't we use this equation here? So let's say that our vx squared, that's going to be our final, and we know that in this case this is 0, right? Because we just said the velocity of y is 0. So now we're going to say that the y is going to be 1 meters per second squared if we're going vx of y squared, or vy of 0 squared. So 1 plus 2 times our g, because we're changing this to y, remember. But our g is going to be negative in this case. So negative 9.8 times, and then our delta y. So basically it's saying, what's our change in y from the original at the start? So Yeah, so basically, let's subtract 1 from both sides, so we get -1, right? It's just simple math over our 2, because we're dividing by this because it's connected to the variable of interest, and so we don't like add it to the other side or anything. And then this equals our delta y. Now, this is going to be a positive number. It's going to be quite small, but let's calculate it. So we get 0.051. So what is the max height? Well, remember that this is the change in y, delta y. So if we want the max height, we're going to have to add it to our starting height. So that's going to be 1 plus 0.051. And this is both in meters. So this is going to 1.051 meters. And that's going to be the max height our car or little thing reaches before. So basically, we found the range and we found the max height. And that's kind of all I wanted this experiment to be, right? Nothing much further, just a couple basic physics equations, algebra based, nothing that requires calculus or anything. So try this at home, try it with your own materials if you want to. There's many more equations and things you can find. You can try scaling it up to the size of like an actual ride. Not making it the size of an actual ride, but using your data to find what like the velocity and stuff would be on an actual ride. But that's basically it. So I hope you guys have a good day.